Okay, so
Okay.
welcome everyone. Thank you, Joerg, very much for joining us, even so late. And today we are happy to have Joerg Teschner, who's going to tell us about geometric characterization of topological string partition function.
Okay, yeah, thanks. Thanks very much for the invitation. So happy to present a seminar this way. Okay, so yeah, what I want to talk about is a proposal for a geometric characterization of topological string partition functions. It is joint work with my former PhD student, Joanna Koman, with Eli Pomuni from Hamburg, and well, a bit more recently, Pietro Longhi joined. And yeah, there are two. Well, okay, can I switch? Oh, now let me see. Yeah, I can switch. Good. Good. So what's the question? Topological string partition functions. Okay, of course. Well, I suppose you guys will know very well. Well, they have various ways of defining them. So typically, or most traditionally, one would start with A or B model topological string on a Calabi-Yau manifold by twisting the sigma model representing strings on such compactifications. And then there is a worldsheet definition of the topological string partition function, which would yield a formal series in powers of a parameter lambda, which actually at some point will be renamed into h bar, which is the topological string coupling constant. And yeah, this can be turned into a mathematical definition through the theory of Gromov-Witten invariance. So I won't go into any details about that. So assume that this is known, but okay, so this gives a formal series. And the basic question is whether there is a way of summing such a series, that is the existence of summations. So in particular, whether this makes sense as a function of lambda, really seen as a variable, and possibly of the other parameters that we have, like the Kähler parameters in the A model topological string case, or the complex structure parameters in the B model case. So that's the basic question. So if we're lucky and if there exists such a summation, then, well, of course, more detailed questions that you may ask are, well, on which space are these functions going to be defined? Or do we really talk about functions or maybe sections of a line bundle or whatever else? Yeah, in at least a class of cases, we shall propose a way to define such summations and an answer to questions like what the geometric nature or the geometric home of these Z top is. So what we're gonna see, and that is of course not at all surprising, is that the Z tops can be defined at least locally. And well, the fun is going to be sort of to explain how to turn it into some global object as functions of, well, for example, coordinates for the Kähler moduli space of a Calabi-Yau X, or of course we can, via the mirror map, think of the T's as being coordinates for the complex structure moduli space of the mirror Y. And yeah, so this is, well, the formulation of a dream, which in some sense, in some way will become true, at least in a class of examples. The dream could be that there exists a natural geometric structure on these moduli spaces, allowing us to represent the Z top, the topological string partition function, as local sections. All right, so here's the class of Calabi-Yaus for which we can say something. I will, or hope towards the end, to be able to mention some hints that, well, the basic picture, although of course not the details of what we have to tell, can extend beyond this class, but this class already is relatively rich and interesting, also in view of some applications. Namely, these are local Calabi-Yaus defined by some equation of the form uv minus, well, some function, rational or polynomial, depending on what case we take, equals to 0. So where we have a locus of the singularities of these Calabi-Yau defined by basically the vanishing locus of the function f sigma, which, well, being variable, well, function of two complex variables, defines a curve in the cotangent bundle of an underlying Riemann surface that we assume to be given once and for all. So these locus of singularities of our Calabi-Yau is a curve in the cotangent bundle of a, well, a priori given Riemann surface C. So this will be called the local Calabi-Yau of class sigma, and well, this may remind of class S, and that is no accident. So class S, supersymmetric, 4-dimensional n equals to 2 field theories can be geometrically engineered within string theory by considering such Calabi-Yaus of class sigma. And for that purpose, or at least for the purpose of considering the simplest cases, those which have gauge groups being products of SU2s, we would consider functions f sigma of x and y of the form y squared minus q of x, where q of x dx squared is a quadratic differential on the Riemann surface C that we assume to be given. Okay, so that is the class of local Calabi-Yaus on which we could, for example, consider the B model. And in that case, okay, we would have dependence on complex structure moduli. So we have a space B, which will be the base of some fibration relatively soon, which is the complex structure moduli space of such local Calabi-Yaus. And well, where do the complex structure moduli hide? On the one hand, we have the choice of the Riemann surface C, which is given a priori, and then over it, we have a quadratic differential called Q. And the space of all choices, that is the product of the space of quadratic differentials on a Riemann surface, or the fibration of the space of quadratic differentials on the Riemann surface over the complex structure moduli of the Riemann surface C. This would be here the complex structure moduli of our Calabi-Yau Y. Good. It is, of course, very well known, and this is part of the, say, Seiberg-Witten geometry, the Seiberg-Witten solution of the class S theories that you could engineer from these local Calabi-Yau manifolds. So this is the geometric structure of special geometry, defined here or represented concretely in terms of a particular class of coordinates, which we could define by taking the square root of Q, which is then the canonical differential on this curve sigma, which basically defines the local Calabi-Yaus in question. So, and then we just consider its periods over, well, some cycles alpha r or alpha r check, giving two sort of dual sets of coordinates, but they are not quite independent. Namely, there is a function f that is the good old prepotential, giving us the dual coordinates a check as derivatives of this function. Okay, all this, I suppose, is pretty well known to you. Here, in order to get this working, we would choose a canonical basis for the first homology of the curve sigma that defines our Calabi-Yau. And so, yeah, then we define the periods, and this is what we can take as a system of coordinates for B, our moduli space here in question. What will play some role is that there is basically canonically associated with these data and with these geometric structures that we basically get for free in this setup is some integrable structure. That is, we can basically enlarge the geometric setup into a torus vibration by basically putting over each point, or well, modulo some singularities where, well, we can put a torus, and the torus in very concrete terms can be defined like here. That is, we take the complex d-dimensional space. D here would be, by the way, if we have here a Riemann surface of genus G with n punctures, then D would be 3G minus 3 plus n. So that is the usual dimensionality of the moduli space of quadratic differentials. And that is what then defines here the dimensionality basically of all the guys which appear in this story. Yeah, and then it's simply a quotient by of the complex d-dimensional space by translations and the, well, say shifted or twisted translations, where we translate by multiples of z to the d with the period matrix. That is the matrix which we obtain by taking second derivatives of the prepotential. Okay, so this is, I mean, modulo the loci where tau, the loci on B, where tau degenerates, where then this torus degenerates, which is some submanifolds of a certain codimension, we have then, so over the so-called smooth points of B, we have then torus fibers sitting representing an integrable structure of the total space M that we shall consider in the following as the main geometric player. So it will be all about the geometry of the space M that we, well, that the following considerations will be concerned. Okay, so this is basically the setup. This is the class of cases we shall consider. In passing, I want to mention, which is partly just instructive or useful extra ways of thinking about these moduli space that we are studying here, and partly it is relevant for some of the remarks I can make in the end. Well, so there are three alternative ways of thinking about our moduli space M, which is our torus vibration representing integrable structure. And on the one hand, M can be represented as a modular space of pairs. Well, there was the curve sigma defining the local Calabi-Yau plus a divisor on sigma. So the divisor is supposed to represent the degrees of freedom here in the torus fibers. And okay, that is of course a very classical and standard story. The able map from, well, complex geometry is the one which would map divisors on surface sigma to points on its Jacobian on this torus fiber theta. So this is just the relation, right? So the relation is just able map. I can think of points on the torus fiber as being represented by divisor or vice versa. Secondly, this integrable system that we're talking about has a reasonably famous and well-known alternative representation as the moduli space of Higgs pairs. So our moduli space M is also the Hitchin moduli space simply. And I don't want to go into much details here, but the map from the Higgs pairs to pairs sigma and D is relatively simple. We can define sigma from the quadratic differential, which is constructed just as 1/2 of the trace of phi squared. So this is the quadratic differential, which would then define here everything as before. And secondly, yeah, we are supposed to define either a point on these torus fibers or equivalently a divisor. Well, for this, we can take the divisor characterizing the bundle of eigenlines of the Higgs pair. that's a bit rough, but yeah, that is certainly sufficient for the purpose of this talk. And last but not least, by a theorem of Diaconescu, Donaghy, and Pantev, this moduli space M, in this particular case of local Calabi-Yau, represents the intermediate Jacobian fibration. So this is just perhaps useful to keep in mind in view of possible generalizations, in particular, maybe some of possible generalizations of the picture we're going to propose might be obtained by, well, more generally thinking of moduli spaces M, which are just the intermediate Jacobian fibrations over the moduli of complex structures. All right.
Joerg, can you remind us what the latter thing means? What is this intermediate Jacobian? I'm forgetting.
Or you're just taking, well, basically you're taking a lattice in the H3. Okay, the details I'm not prepared sort of to quickly. So you're basically dividing the H3, the third cohomology. Well, there is a.
Sorry. I see. So you just want to generalize the usual Riemann surface stuff that comes from, this family of Calabi-Yaus to more general Calabi-Yaus. That's the whole
That's exactly it, right? Okay. Exactly. So for more general Calabi-Yaus, basically it would amount to sort of here replacing the H1 by H3 and so on. But of course, yeah, then you.
Yeah, I just forgot momentarily what the story was about. So, yeah, great.
And then you are to divide it by a lattice, and that is what is called the intermediate Jacobian. All right. So, I mean, in some sense, our strategy was, at least at the beginning, relatively simple-minded. Namely, at least in some cases, one is able to compute because some of these local Calabi-Yau can be represented as limits of toric Calabi-Yau. So one can just compute. There are well-known tools, notably the topological vertex that, well, Mina and collaborators have pioneered. And even though this is not applicable, at least to the best of my knowledge, or has not been applied to all local Calabi-Yau of this class, at least in some cases, and these are sort of prototypical examples from which one can learn a lot. It does work and one can apply it. And yeah, then simply our basic idea was to compute and just look, is there some, I mean, in the results, is there some maybe natural geometric structure which would summarize the results or which would govern the results? So let's see. I mean, this presumably many of you have known in one way or another already. So in the basic example that in the end of the day will be associated to a 4-punctured Riemann sphere, one could start by considering toric diagrams of this type. And then, yeah, the topological vertex gives a, well-known recipe to associate certain functions to the vertices of this diagram. And then for each internal leg, there is supposed to be a summation over Young diagrams. And by this, basically, this picture defines, well, a big sum over Young diagrams where one can perform most of the summations, not all, but most of the summations. And this leads to a structure for the answer of the topological vertex of this form. There's some factor which basically one has to add by hand, which has to do with some residual normalization freedom that one has here in this game. And then this would correspond here to a cutting basically along a vertical axis. So it corresponds to performing the summations here, 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 and so on. So this would go into Z in, where one has basically 1 and 2 as the variables contained in part of the answer. And here's another part, say from the left part, which would give Z out. And then there is some part which contains basically the sum over the here these internal, well, the variables associated to these internal edges here, connecting the left and the right half of this toric diagram. This goes into what is called Z-inst. And that's a pretty well-known guy, namely that is turns out to be, and that is already known for a while, the 5-dimensional n equals to 2 SU2 instanton partition function as defined in the works of Moore, Nekrasov, Shatashvili, Losev, Nekrasov, Shatashvili, and Nekrasov. And good, what is of particular importance are also here these normalization factors which appear here, which, okay, play some role, and we will see part of that in a moment. All right, so that is, well, partition function for a toric Calabi-Yau in order to get here our friends, the Y sigmas, the local Calabi-Yau, which are associated to 4-dimensional supersymmetric field theories. One has to perform a limit, which is done by parametrizing these, well, the Q's were parameters for Kähler parameters Ti to begin with, and assuming that the Kähler parameters are proportional to some joint parameter R, which is then sent to 0, defines the limit which brings us from 5D to 4D. And this would give then, say, the mirror of this Calabi-Yau, which is known. One could write down the equation easily. This would then turn into the equation that we have here when Q is a quadratic differential on the 4-punctured square. Okay, so all this is, I think, pretty well known and good. And let me furthermore note that it is also known that this 5-dimensional instanton partition function that one simply finds in the result, when we take this limit to 4D, it turns into the conformal block of the Virasoro vertex operator algebra. And if we are not doing any fancy games like refinement or so, it would be at s equals 1, the Virasoro VOA. So yes, the structure in the 4D case will be the same. One can indeed perform the limit of these factors. Well, the definitions of the special functions which appear there, they're given here, but they don't play a very prominent role in my talk. So yeah, one has something pretty explicit to work with, and that is what you could take, or what we did take as our starting point. Okay, what is perhaps a little less well known and perhaps a bit more interesting then is there was a kind of cute proposal or prediction from a work of Dijkgraaf, Holland, Sulkowski, and Wafa using a certain chain of dualities which would relate the Z top to another object, which was also, I mean, variants of that, not exactly the one that we have in this case, but variants thereof are called dual partition functions by Nekrasov and Ukunkov, and they're obtained by basically taking kind of transform. In fact, if zeta here is purely imaginary, it would be a Fourier series transform over the Z top, our main object of interest. So this would basically, preserving information because it's an invertible transform, produce another object containing the same information that we call Z dual. And well, I have to skip a long story. I mean, there's a lot of amazing discoveries here behind this, I mean, which I'm summarizing here very briefly. There is the reasonably famous MNOP correspondence, which would relate the Z top to a object in Donaldson-Thomas theory, counting D0, D2, D6 branes. And from that point of view, this dual partition function would then count configurations of D0s, D2s, D4, and D6 branes. So it's a counting D brane or counting BPS state object that appears here, which in some sense I think is what is behind some of the following proposal, some aspects of the following proposal. Anyway, for the moment, it's just a transformation, and the prediction of Dijkgraaf-Holland-Sulkowski-Waffer was that this object here can be represented as the free fermion partition function associated to a non-commutative deformation of this curve sigma, which was defining our geometry in the first place.
This is actually older, Joerg. The connection to free fermions arose first in the paper that I wrote with Marcus, Albrecht Clem, Kumran, and Robert, where we first explain how to for these kinds of curves, these kinds of Calabi-Yaus that arise from 5-dimensional gauge theories, or that are related to 5-dimensional gauge theories, or rather, more generally, 5 mirrors of toric Calabi-Yau manifolds. So take any toric Calabi-Yau, take its mirror. We explain how one can formulate the B model as kind of a computation of a free boson on a quantum curve. And then we also explain that if you do this kind of sum, that by the usual sort of relation between bosons and free fermions, then you should get a free fermion partition function. This is simply like a relation, the fact that in the free fermion world, you're supposed to sum overall momenta, and that was that relation. The story of Dijkgraaf and Holland and Sulkowski and Waffer is later, and the interpretation in terms of D6 and so forth is later. But the connection to free fermions goes back to our original paper. So it's not a big deal, but it's
okay. Sorry. Yeah. Then indeed.
Because you're reviewing history.
There is a. Okay. It tells.
It's all,
we were not digging deeply enough into all the. I mean, rather overwhelming literature that has accumulated. I'm sorry about that. This version is what we found in the reference mentioned here. All right, so I was about to explain what means non-commutative deformation. Well, that is also, I think, an idea which has become rather familiar and rather well known by now. And good, Mina can tell me where exactly the root is. Probably, presumably, it is the paper that you wrote with.
It's the paper that I just mentioned.
And it's the one. Okay, yeah, okay. So it is basically, well, if we have here an equation defining this local Calabi-Yau, well, then the canonical differential basically introduces a natural symplectic structure that you can use as the basis for a quantization. And for that particular case here, it would simply mean we would be instructed to turn the y coordinate into the derivative with respect to the conjugate variable x. And this would mean that the equation y squared equals q of x would turn into some differential equation defined by the differential operator, which is written here. And such differential operators, well, this we know from, these are basically those from Schrödinger equations, but a bit more geometrically, they can be thought of as representing paratransport of a very specific class of holomorphic connections, which nowadays are typically called operas. That does play some role for some of the following. So, I mean, it's not hyper prominent, but yeah, it is of some relevance. Good, and here I'm cutting a moderately long story brutally short because it's not supposed to be the main subject of the 2 days talk. The object that we have defined here, which is simply a transform of the topological string partition function, can indeed be shown, and that was sort of our first step in the paper with Joanna and Ellie, can indeed be shown to be, on the one hand, equal to a math object called isomonodromic tau function, which is just the tau function that is associated to the classically integrable equations describing deformations of such differential operators. Well, more precisely, there is a canonical deformation a further deformation that we have to do, which I will make explicit a little later, in order to just have sufficiently many variables to play with. And having therefore then the variables zeta, which appear here, actually represented as variables of the differential operator that we're talking about. And then we can study the ways of deforming these differential operators with respect to underlying complex structure in such a way that the monodromy of the differential operator stays constant. So that is a famous classical mathematical problem, the problem of isomonodromic deformations. The names going with it are Garnier and then many others. So that defines an object called the tau function. And what we have shown in this first paper was that the Z dual, and this uses basically this chain of discoveries that I mentioned in a very important way, so that this is equal to the Z dual that was defined here above. I should also mention what was important for that was the discovery going back to Gamma-Yun, Jorgov, and Lissovy, which was then, which was in the first place a conjecture, later proven by Jorgov, Lissovy, and myself, which basically was telling that, was showing that a very similar transform applied to the =1 conformal blocks is a representation of this isomonodromic tau function. And now, we just look and see, it's just exactly the same that we find here in order to see that the Z dual is the tau function, and good. And then, the whole story can be somewhat refined and improved. And it can be shown that the tau function is apparently basically all of the tau functions that we know have a free fermion representation, so it indeed is a free fermion partition function. And what we made a little more precise and what we elaborated a little bit was that indeed it is naturally associated to the non-commutative deformation here of the curve sigma, that is to the quantum curve, the tau function that we find here. So this is okay. I don't want to go into too much of details about that part of the story. It is basically to say, we find known objects, the tau function, and indeed this prediction of the string dualities was here basically confirmed mathematically by just calculating and putting together the pieces. And then it's in the end of, say, math theorem, if you like, that indeed this duality prediction is fulfilled in this case by the chain of all these results. In some sense, one way I sometimes like to mention, or one way of thinking about it I like to mention, is that, after all, dualities are reasonably deep conjectures typically, and here I would say this provides a rather quantitative, detailed check of all these duality conjectures underlying this prediction.
So, can you?
Okay, maybe I should stay there then, if there's a question about it. Yeah.
What do you mean by the tau function? Some object that satisfies some infinite set of differential equations.
Right. So you could here define it through some differential equations. Basically here, you could rely on the definition of the tau function through the nonlinear partial differential equations that govern the isomonodromic deformations of such differential operators. That is a definition of the tau function that we could use. Of course, alternatively, you could define it through through the free fermion partition function. It depends on which starting point you prefer. But here, a very concrete way of defining it would just use basically the deformation theory of the quantum curve.
when we talk about the tau functions, you can think of it as just a partition function of some of fermions, possibly an ordinary free fermions, but.
Can you say again? There was some problem with the acoustics. I couldn't quite hear what you were saying.
Can I equate the tau function with the free fermion partition function and just simply think of it that way? Now we'll have to say what kind of fermions, because they're not, I guess, ordinary fermions, because you have to get an H bar into the story. But
okay, yeah, I mean, good. I can say maybe a few words. So we would be talking about free fermions, well, non-abelian free fermions, and that's perhaps a new twist. It was, I think, not so much developed, and that's a little bit what we developed then in our paper, in the first paper. So it's basically two-component free fermions on the underlying surface C with a non-abelian monodromy that we need. And then it's a partition function basically of a system of free fermions twisted by a local system on a Riemann surface C, which, however, then is non-abelian. And it can also be represented by some Fredholm determinants and so on and so forth. So there is a certain bit of mathematics that you could use to represent this tau function it is similar to many of the tau functions, but the difference is here somehow in the non-abelianness. So, well, I don't know if this is of any use. I could try to elaborate, but on the other hand, I really would like to go a little bit in another direction in this talk. So
that's fine. So just a comment. So in our story, we had these free fermions on upstairs, not on the C, but on sigma, and they behave like ordinary free fermions, except that they're 2-point functions. If you take them from a patch to a patch, they transform by basically Fourier transform. So they knew that that's how quantum mechanics sort of arose.
Actually, this is a very interesting thing, which I think, well, we should think about further. This, of course, I guess is cleanest in the toric case. We're taking here this limit, bringing us to these class sigma cases, in which case, well, the picture I have, but this should be made more precise. The picture I have is that this limit turns these basically non-commutativity that you mentioned into this, well, what remains is this two-sheeted covering structure. And in the end of the day, to really describe sort of non-perturbatively this quantum deformation, this non-commutativity, it's best to think about it not as fermions living on this curve sigma that we start from, but somehow, well, the quantization, after all, of the curve sigma makes it, well, blurred, non-commutative, and so on. Heisenberg hits us here. And that the result is best described in terms of a non-abelian connection on the base curve C. So this non-commutativity basically replaces abelian fermions on sigma by non-abelian fermions on the base curve C. And I think, well, this is probably the deep reason for what we found, namely that there is abelianization happening here. It is relevant for our story, the abelianization of Lotte and Andy will occur or will become relevant at a certain point.
Does this tau function have a simple interpretation in the classical limit?
The tau function, yes. This is remark I wanted to make in the end. So let me make it in words here. And perhaps if you want to see more, there is a kind of backup slide at the very end of my slides that you can probably look up already if you want, where this is made more precise. The tau function basically in the classical limit turns into a theta function on these, well, intermediate Jacobian fibration, or this, well, the torus fibration that we have here, which I think is a very interesting observation by itself.
But you should get, if by the classical limit, you mean essentially you pick out the one loop amplitude. Then it should be just the ordinary free fermions, so just the vanilla free fermions that you get from this graph.
Right. Yes. And I mean, somehow, okay. And what we find from our result is if you just take here this tau, which of course here somehow secretly has a h bar in it, and if you take the h bar to 0 limit, then as the leading term, well, as one of the leading terms, well, the leading term is of course again prepotential, and then there's a subleading term which is this theta function, and this is just the ordinary theta function that you would just expect on the basis of your arguments. So the interesting thing is that we here identify very precisely how it is deformed by further h-bar corrections.
So this just means that in terms of the Seiberg-Witten fibration, this is just a canonical coordinate on the fibers. That's what this theta function is doing.
Yeah, so right, so the zeta here, and it will become a little more precise in a moment, would then be represented in this limit indeed by one of the linear canonical coordinates on the fibers of the Seiberg-Witten fibration. As I said, if I have time, or there is going to be a slide which we can look at together at the end, or there is a slide that you would find in the well, in the talk as it was uploaded, as far as I understand. We can come back to this if you want. Yeah.
Can I ask you something simple? I don't know, probably you said among your words something related to what I'm asking. So, but is this tau function expressible in terms of Fredholm determinants?
That comes here. So this is sort of the first remark on the next slide. Yes, this tau function has a Fredholm determinant representation. Basically, it is reflecting this cutting here that I mentioned, and then there is some, well, yeah, okay. No, I really don't want to go sort of into too much of details, but I do want to mention that it has a Fredholm determinant representation, because what this allows us to prove essentially is something that from the topological vertex was never terribly clear. The question is if all these summations do converge in the end. Of course, everybody was hoping, I guess, that they do, but well, some honest people like Giovanni Felder with a student tried to prove this directly, and it is terribly hard, it turns out. And I think even for this case, the results were not available up until recently. And good, here, of course, having a Fredholm determinant representation gives a very neat way to make sure that this is mathematically very well defined and has nice analytic properties, etc. So here it comes via the Fredholm determination, Fredholm determinant representation of the tau function, which then, by basically inverting this transform, implies similar results for the z-top itself. Okay, so, and in particular, what this what this allows me to show is that both the dual and z-top are locally, at least, holomorphic functions of these variables t. But yeah, the whole question really I want to raise and discuss here, I'm proceeding a bit slowly, but I hope I ultimately gonna get to something at least, is yeah, how does this globally continue? Sorry?
Our talks are typically extremely informal, so we go on until the speaker is exhausted. I'm afraid that because you're joining us from Europe, you are going to be the limit. So we'll try to be gentler then.
Yeah, it's probably going to be, if the talk degenerates, then just stop me in one way or another. Just stop me. Okay. In any case, yes, I want to stress that, of course, just from this, this type of representation by topological vertex and so on, what is already known is that the partition functions are only piecewise holomorphic over the moduli space. And there's the basic example. Here, returning to, say, the toric diagram, we could do flop transitions, which would relate chambers in the Kähler moduli space. Like, for example, here, this would be, of course, just a part of the toric diagram. And this would represent, say, the results in a chamber where this variable Q has absolute value smaller than 1. And if we want to know the result in a chamber where Q absolute value is bigger than 1, well, this is another part of the generalized Kähler moduli space. Then we would have to use this flop transition. And well, it turns out, and basically can be shown with this topological vertex method itself, that the partition functions change, but here in a relatively simple way. Namely, this precise statement is that the analytic continuation from one chamber to the other is related to the actual value as you define it through the topological vertex by a relation like this. So it picks up an additional factor, which is the ratio. Well, actually, I think, sloppy with the notations. It should be the same M functions that was defined here. So some special functions that in the 4D limit give some Barnes double gamma functions. Okay, so basically, when we cross this wall, which corresponds to Q absolute value equals to 1, a jump happens. That's another way of saying it, with this factor describing the jump. Good. We were just to avoid confusion. If anybody has looked into the literature, in some of the older literature, it was claimed that there is flop invariance of the result. Well, it turns out if you look a little more carefully, that's not quite true. There was some business with the infinite products, which led to such a result in some earlier literature. The precise result is, as we say here, this is really what happens. So, okay, that's of course from many points of view not unexpected. This means there is some wall crossing when we cross walls between chambers. And here is a simple example that basically we can compute directly with a topological vertex. However, in our case, still with a bit of reflection, one would see this would still not allow to extend over all of the moduli space. So the question is, how can we continue it? Is there a way to describe it really globally over all of the moduli space, which after all, we have a concrete representation, is the space of pairs Riemann surface quadratic differential in our case. What we observed in the first paper was that the results that we find in this way, they have a neat geometric pattern, which basically reflects abelianization as discussed by Hollands and Knightsky. Let me leave it here with this as being a side remark, which in a different form will be made a little more precise later. Because, well, basically the new stuff gives a better way of understanding this. Good. And now let me take a breath and try to formulate in a somewhat abstract form the ultimate proposal that we arrive at, which we can check and substantiate in the examples I discussed by some concrete and explicit calculations. So the main geometric players are here, as introduced before, the moduli space of complex structures and a torus fibration over the space of complex structures which is defined by just basically, well, the intermediate Jacobian fibration. So it is the one canonically associated to the special geometry of the base manifold B. The claim is, or the proposal is, that then there exists a canonical one-parameter family of deformations of the complex structures on M, the total space of this torus fibration, defined by some atlas of Darboux coordinates on something which is related or essentially equivalent to the twistor space over this space M. And these Darboux coordinates play the key role for the following story. That is, we think of, well, some system of patches by which we cover our moduli space M, the main geometric player, the torus fibration, and we're then giving it a family of deformed complex structures in terms of Darboux coordinates that we can define on this space. And of course, already this may remind you of GMN's story, Gayoto-Bornaitsky's story, and this will become more precise in just a moment. But so this is good. Part A basically is going to be GMN in essence applied to these manifolds M which appear in our context. But what's now really bringing in the tau functions is that we propose that there is a canonical pair of a line bundle on this twistor space. And we're going to talk about how to describe the transition functions, namely in terms of something we call difference generating functions, which is something that is going to be really completely defined by the changes of coordinates between the patches. So to the changes of coordinates between the patches, we're going to associate difference generating functions. And these are just the transition functions defining the line bundle. So it can hardly be more natural than that, except that I didn't tell you what I mean by difference generating functions. And then there's furthermore, connection on this line bundle, holomorphic connection, which is such that the flat sections would be our tau functions. And having this, in order to get the Z top, all I have to do is to exploit the fact that here I'm assuming to have a polarization for my Darboux coordinates, a splitting into basically coordinates and momenta. I'm Fourier expanding with respect to, say, momenta, but of course I can swap the roles of momenta versus coordinates by another Fourier transform, and the Z top is a function then of the coordinates. So this magic formula again appears here, it is defined in terms of this polarization that we may have for the Darboux coordinates. So this is already basically the proposal in a nutshell. But yeah, I'm owing you several further explanations, in particular how to describe these changes of coordinates, what type of changes of coordinates do we have, because the claim is that in the end of the day, basically everything is terribly canonical, and there's basically zero choice in these data that define everything. Okay, so the first part here, that is basically the part A of the proposal, is to define H-bar deformed complex structures. So this is how the topological string coupling enters. H-bar was previously called lambda. And this is done, okay, by some atlas of coordinates, where I have Darboux coordinates, so with symplectic form of the standard type in each patch, such that the changes of coordinates are of cluster type. So they're defined here by, well, these simple formulae that you may have seen already in other contexts. In terms of data, omega of gamma, so we're choosing some labeling of the coordinates by, say, vectors in a charge lattice, for which we have chosen a very concrete basis like here. And good, then there's an associated symplectic form, which allows us then, for example, to make the labeling of the coordinates by these charge vectors very explicit here. So we can, if we want, think of very concrete tuples of coordinates xi with upper index r and x check I with lower index r. And here are the formulae from the transition functions, which are of standard cluster type with these only, say, undetermined data in this formula being these Donaldson-Thomas invariants, which are data satisfying the Kontsevich-Soibelman wall crossing formula. So this is the form of the transition functions defining our geometry. And these here are coordinates xir are functions of, well, on the moduli space M on our torus fibrations, so which furthermore are functions of h bar, which have a asymptotic expansion when h bar goes to 0. And here's the leading behavior that they are supposed to have, which is 1 over h bar. So the leading term is given by the period coordinates that we have seen before. And then there is a subleading piece, which somewhat interestingly is associated to coordinates on the torus fibers in our torus fibration. So this specifies the asymptotic behavior for h bar to 0, the classical limit of our coordinates. In essence here, what I'm telling you could be summarized by saying that basically the part A here of our proposal is what you could call the conformal limit of the GMN story of Dabou coordinates on the manifolds M, which classically have the structure of a torus fibration. Good, so I'm staying basically here with describing the part A by, on the one hand, reminding, if you know about this, or telling, if you don't, how such coordinates can be found. So what I'm postulating here as conditions that the coordinates have to satisfy, this can be formulated a bit more sophisticatedly as a Riemann-Hilbert type problem, and this is the way it has been formulated by Gayotto-Murnitsky, or more recently by Tom Bridgeland, really for this conformal case. So this problem of Riemann-Hilbert type, where basically we replace the usual well, linear transformations describing monodromies by this jumping behavior of the coordinates, these symplectomorphisms. So this has a solution of the following form. It has a solution in terms of nonlinear integral equations, where here in particular these Donaldson-Thomas invariants enter very explicitly. This is not going to be the description we shall be using very much, but it's perhaps useful to keep in mind that such a description exists and could be applied in principle to our cases as well, where in particular then of course all this machinery around wall crossing formula and so on, Donaldson-Thomas invariants is relevant. In our case, it seems more natural to describe the second way of solving this Riemann-Hilbert problem, it's called BPS Riemann-Hilbert problem here, namely basically in terms of the quantum curves. So the idea here, and that is also not a new idea, but perhaps some aspects of how it is applied are new. The idea is that the coordinates that we're after, the coordinates which are supposed to jump in this way, can be represented as monodromy data for differential operators of this form. More precisely, we want that everything is defined basically as canonical as possible, as functions locally defined or locally over this base manifold B in particular. And what allows us to do that is to by defining these coordinates in terms of the Borel summation of the exact WKB solutions to the differential equation that is defined by this differential operator. I will be a bit more precise and remind some of the basic definitions in just a moment. But the point is, yeah, this Borel summation works basically patch by patch over our manifold B here, which after all is represented by the choice of a quadratic differential on our Riemann surface C. Okay, and yeah, what this leads to is a concrete description of the charts that we can use, the charts to which we associate here our coordinates. In terms of the so-called spectral networks, that is certain graphs that we can draw on our Riemann surface C, the one that we started from, the one on which these differential operators live, which are basically defined by these, the Q in a way I shall describe in a second. Okay, so here a few more details on the well, quantum curves and how they are used to define the coordinates of our interest, the Dabou coordinates that are the main input to the definition of the tau functions in our proposal.
So just quickly, what do you mean by the conformal limit? Just the fact that you want to study the like the four-dimensional curves or the Hitchin system itself?
No. Yeah, conformal limit means when I study the Hitchin system, we usually have, well, Hitchins as equations as a pair of, no, I mean, these are non-holomorphic equations, right? So where we have, I mean, the self-duality equations are non-holomorphic equations. And we're taking the limit in which the connection becomes holomorphic. Right, so the, well, I mean, Hitchin's equations are the equations for flatness of a connection on the Riemann surface, which generically is not holomorphic. Like in Chicotti-Vafa, TT star, in the generic case, you're thinking about non-holomorphic objects, yeah, but then there is a limit which you can take, which is you have these two parameters. There's a parameter R, which we get by scaling the Higgs field. And then there's the hyperkähler parameter, call it zeta. And then you can take a limit where R goes to 0 and zeta also goes to 0 in such a way that the ratio stays constant. And that is the conformal limit, because then it leads to a description in which, well, the connection that you're talking about becomes holomorphic. That is, rather than talking about non-holomorphic connections on the Riemann surface, we would be talking about the pair of a holomorphic bundle E and a holomorphic connection, I mean, 1,0 part of the connection. This is the data that remain basically in this holomorphic limit. Gayotto has, well, first discussed this, and then Andy and collaborators have well, some mathematical theorems on how to make this in the context of the Hitchin systems.
And in principle, for this theory that you're studying here, like Seiberg-Witten with 4 hypermultiplets, there the BPS spectrum is known, right? So
yeah.
So in principle, all the omegas that you need in this formulation are known.
Right. Yeah. Yeah. And in some sense, okay, what we're using is the description in terms of the quadratic differentials and spectral networks, but of course, others may be, other descriptions that are known may be useful for some aspects of the story. Yeah.
So here the omegas are the 40 BPS state counts which do wall cross, whereas the topological string partition function, which is supposed to be an equivalent encoding of all of this, is really 5D BPS state counts that don't wall cross. So are you saying that you can compute one set from the other set, or?
Okay, so first of all, of course, in the end, the proposal, I mean, we can verify the proposal in 4D case. I suspect that there is a similar story, but that remains to be developed in the 5D case. You said that the 5D partition functions are not supposed to wall cross. Well, topological vertex proves that this is not the case. They do wall cross. And here is the relation. Here's the relation that you can prove already in 5D.
This is misleading. You expect much worse wall crossing.
Of
Basically,
course.
more anomaly, right?
No, I mean, of course, I mean, this is just a very simple example due to, well, a simple type, I mean, which happens at a simple type of transition, yes.
So are you saying that these GMN transformations or the conservative solvent are supposed to take care of that? That they will encode they'll you certainly don't expect a holomorphic function, right? Because of holomorphic anomaly. You can make a function, but it's not holomorphic, right?
Right.
And are you saying that there should be an equivalent formulation which uses this conservative Soibelman wall crossing, which is relatively like cluster type and simpler?
Yeah, I guess that's a way of saying it. In fact, yeah, this seems to be a way of saying basically the punchline that sort of we're gonna cover the whole moduli space by locally holomorphic, I mean, by patches in which the tau and partition functions are locally holomorphic, but then they jump across the walls in a way which is exactly dictated by these symplectomorphisms.
But it's still confusing because all that holomorphic anomaly is a statement that the topological string partition, the moduli space is like a phase space.
Mm-hmm.
And you can understand a holomorphic anomaly as saying that you just have to find the right coordinates, and the transformations between the coordinates are not simply, you know, changes of variables, they're Fourier transforms. So now we seem to have three things.
Well, I mean, I would say that I think what we're proposing here is a way of making this mathematically precise. So we have here precise changes of coordinates, which then will govern the way how the partition functions jump from one patch to the other.
A holomorphic anomaly is also precise, and the relation to sort of...
Okay, I mean, we don't have the...
So I wrote a paper long ago with Clem and Vincent, where, you know, we gave out a general theory, but we also studied concrete examples, in particular Seiberg-Witten theory. Mm-hmm. And when these are fairly non-trivial calculations. So.
No, I mean, okay, so remark one to be made is that the precise comparison of our proposal with what holomorphic anomaly tells us is something that remains to be done. This proposal that I'm formulating is checked basically against these topological vertex computations. So we do have especially these 4-punctured sphere or 4-flavor SU2 Seiberg-Witten example, where it precisely reproduces what we find there. Well, we also have the pure SU2 Seiberg-Witten, which is in some ways quite instructive and so on. So
maybe look at our paper, because I mean, holomorphic anomaly literature is a little bit opaque because the calculations are really hard. But I think we explain it fairly well. So.
Well, okay. In any case, it's on my to-do list. Here, of course, I'm stressing everything is going to be non-perturbative in H bar. It's not using an expansion in H bar, right? So everything here is non-perturbative in H bar.
I see. So that's really interesting. I see. Yeah. So certainly everything about holomorphic anomaly is completely perturbative.
This was my understanding.
I see. Oh, fantastic. Okay.
So in particular, you see, you would not, I think you would not see in the perturbative expansion here the role of these Kontsevich-Soberman symplectomorphisms. They would just be replaced by ordinary Fourier transforms. So a lot of what is non-trivial here about the non-perturbative thing, I think, is going to be hard to see in the H bar expansion.
And Now, from this, do you get a formulation? Is it enough to know omegas and then you know everything? All genus?
Can you say it again? There was again some.
If I give you the list of all omegas, is one able to reconstruct the full all genus non-perturbative topological string partition function? Is that enough, or do you need more?
In essence, that is our claim, although concretely we're doing it in a somewhat different way. I mean, of course, yes, you could, for example, just plug them in here and thereby define the coordinates through the GMN nonlinear integral equations. However, we are focusing here on the use of the quantum curves for the discussion. But in principle, I mean, morally speaking, this is exactly what we are trying to say. Okay, so yeah, maybe, is there other question?
Yeah, just to restate that question, if I give you the BPS state counts associated to like type 2A on one of these local Calabi-Yau threefolds, then that determines the BPS spectrum of M3 on that same threefold? Because in this way, where you plug in the omegas into this integral equation, take the conformal limit, and then relate them to the topological string partition function via this tau.
True, yes. Right. You see, we're using these guys because in the WKB, basically, these omegas are encoded, right? So we find it more convenient to work here with these differential operators, whose exact WKB, of course, encodes all this that we would need to know following this approach.
Is that map supposed to be invertible, where given the topological string partition function, one can recover the omegas?
Whether we can recover the omegas, presumably yes, because it would be, I mean, okay, it's not the way we have organized things, but it is in the it is, of course, in the information contained in the H-bar expansion, which is what you can do once you have the topological string partition function.
I don't know that this is.
Okay, that's not the way sort of we approach the thing. That's not what the way we're doing it.
Yeah, I mean, it would be. I wouldn't know how to, for example, recover information about, say, counts of D4 branes or higher dimensional branes. D2 and D0, yes, but in some sense because they're curves. But saying that one can actually also understand the count, the numbers of BPS states of D4 branes on compact 4 cycles. I wouldn't know. I think that that's more information that topological strings should have.
That's why I'm surprised, because it's.
Okay, yeah, maybe I move on.
I think the wall crossing is strictly more than holomorphic anomaly. That's for sure.
I mean, the wall crossing, of course, here it has the two aspects, right? So there is what GMN called the K-wall crossing, which is what happens either with respect to H-bar or if I move in a corresponding way on the base B. That is one thing, and on the other hand, there is then the crossing of the walls of marginal stability, right? So both are relevant in a way here.
What is the K-wall crossing?
Oh, this is just, well, these jumps basically, that is, they can happen on the one hand, I mean, these happen with respect to H-bar across the rays, which are associated to here the phase of the periods for which there is a BPS state. So if there is a gamma associated to for which the omega is non-vanishing, then across such a ray in the H-bar plane, these jumps will happen. Of course, this is, I mean, equivalently, we could move with on the base by changing the coordinate a gamma in such a way that we cross such a ray. And this is what GMN called the K walls, because these are walls not then in the H bar plane, but these are walls where coordinate changes happen with respect to changes on the base. That is, we have we think of the base as being decomposed into chambers, which are separated by walls across which we have such jumps.
And one more question: when you consider omegas, do you consider all possible central charges, like you go all the way around in a complex central charge plane, or just some half plane?
No, I mean, we can, I mean, here, of course, yeah, it's just a description in terms of, well, a decomposition of these base times C star into some chambers which are separated by walls, and we're not restricting to a half plane for that purpose.
So debranes and anti-debranes are considered democratically.
Yes. I mean, the punchline simply is here that, yeah, it is the BPS spectrum determining these coordinates, right? So this is, I mean, this is as in GMN, basically. And the news is sort of how this can determine the analytic properties, in particular the jumps, the wall crossing of the tau function on the one hand, and then relatedly of the topological string partition functions on the other hand. That is sort of where the story goes. Yeah. Okay, so let me continue a little bit, perhaps. So here, this is to make a little more precise how to think about these quantum curves. And I mentioned already that beyond what I called the canonical quantization, which is simply replacing the y squared by the differential operator, we have to do a further deformation in order to account for these extra variables that we have in the partition function. So let me go back just to remind you. We saw here these zetas. The zetas appear here in the transform. These are some new variables, and well, it's kind of obvious. The t's, after all, they correspond to the variables in the Q, the complex structure moduli. So if I want extra variables, the zetas, I somehow must deform the Q or the quantum curve even further. And what is kind of beautiful in this case is that it turns out that the way to do it is essentially canonical. There's basically little choice. It is simply by, well, some further H bar corrections, but these are pretty canonical. Namely, these are represented by what is called apparent singularities. Apparent singularities have the property that essentially they don't change the monodromy of this differential operator that we have here, where essentially means the monodromy projected into PSL2C is, well, I mean, trivial around, say, x equals to u. There's a -1 if I consider it in SL2C. So such a singularity is called apparent singularity. It is characterized by two parameters. One is called u here, and the other is basically the residue at x equals to u, that is called v. And these, in the end of the day, form a canonically conjugate pair with respect to a natural symplectic structure in this problem. So these are also Dabou coordinates for basically quantum curves. And the u and the v are related to the original Q, the one we started from, the one defining our curve sigma, by a very simple equation, which is just this one here. So basically, just from what I'm saying here, or from looking at this example, what we can see is that these variables determining these deformation, the apparent singularities, this pair u and v, so what it defines is a point on the curve sigma. Well, they're satisfying this equation, which is just recognized as the equation defining the curve sigma, which on the other hand is exactly what we need to ensure that this is an apparent singularity in the sense of having trivial monodromy around x equals to u. So the pair u and v defines actually a point on sigma. So this is what defines the divisor D, right? So the extra data here that enter into this extra h bar deformation are really nothing but the choice of a divisor D on top of the curve sigma that we started from. And this in the end is just the way that we need in order to account for these extra variables zeta, which we have here in the dual partition function. So the same zetas as appear here in the transform. So they're just all related to each other. Okay, so this just to make our ideas of the quantum curves that are relevant here a little more precise. So these are operas with apparent singularities.
So you are adding on a genus G curve, you would add G such points.
3G minus 3 plus n if I have n punctures.
3G minus 3 plus.
Yeah, it's just to exactly account for the dimensionality of the space of. So I need
with 4 punctures. So
yeah, here we have 4 punctures, so it's just one. This one extra variable is what is needed.
G is the genus of C.
G is the genus of C. Yes, that is right.
Okay, and from Liouville perspective, these apparent singularities are degenerate fields, or what?
Yeah, there's a relation between apparent singularities to degenerate fields. That's true. We're not going to need this here anywhere, but it's true.
So I can think of it as and of course you add C is equal to 1, so it doesn't matter which one you add, right?
Mm-hmm. Mm-hmm.
Okay.
Exactly. Yeah. Yeah. Well, that's of course can be useful. Yeah. Okay. So the conjecture here, or well, part of that is actually a theorem by now, is that the solution of this BPS-Riemann-Hilbert problem as formulated previously is given by the composition of the holonomy map with coordinates on the character variety. That is just, well, we're taking the traces of holonomies in order to get, well, coordinates on the space of monodromy data. But, well, the point is here that we want to identify special such coordinates which have Borel summable H-bar expansions. This is not going to hold in general, and that is going to be strongly dependent on where, in which patch, in which chart, in which place on the base defined by these quadratics differentials I am, whether a given set of coordinates on the character variety will have Borel summable H-bar expansion or not. Okay, so something about this story, that is exact WKB, etc. What we need to know about this. So we're looking here, that's our quantum curve, and it defines a differential equation, a Schrödinger type equation. Of course, the formal expansion in H bar is pretty well known, that it's a WKB expansion. And the way to describe it here, which is perhaps most convenient, is through, well, an intermediate object S. So basically, we first solve what is called the Riccati equation in order to define a function S in terms of QH bar. This equation here can be solved in a formal H bar expansion like that, and then there's just recursion relations defining the higher SKs in terms of the lower one, with the leading one just given by the square root of Q. And there are apparently mathematical theorems, although as of yet it seems the situation in print is not completely settled yet, but I think that's just going to be a matter of time until the relevant results will appear. It is believed that this series here, which is the series defining the solution of the Riccati equation, is Borel summable away from Stokes lines. Stokes lines are the lines defined by, well, the equation that the imaginary part of the coordinate I can define from the canonical differential by just, well, taking its primitive, and then I can tilt it by some angle given by the parameter lambda or h bar, so that this is constant. Sorry, here is actually, yes, indeed, the lambda should be h bar because, yeah, the Stokes lines for this here, they will depend on the phase of h bar, and this is what explains here this factor by which we would tilt the direction of the coordinates, that is the direction in which these lines run. Okay, so what's the picture I should have in mind? We have on our curve C then defined the Stokes lines, which are just curves defined by this equation. They decompose my surface into regions. I will describe a little bit how they look like in a moment. And in these regions, I do have Borel summability. And yeah, what then can be considered, and that is an important part of the story of exact WKB, are the so-called Walsh symbols, which is just we're taking here, well, the full sum. We're taking the odd combination to make it odd under the exchange of sheets of the covering. And these guys can be Borel summable. And when they're Borel summable, and well, as I said, the criterion here essentially is what is probably proven in the work of Koike and Schäfke, and there is work in progress. Part of it has appeared by Nikolaev, which claims equivalent results.
Is there no information in the even part of S?
There is information, but well, essentially, no, not more information. So, because okay, so the Borel summability depends on the topology of the Stokes graph of the graph formed by the Stokes lines. And here are some pictures for how they can look like for simplicity and sort of as a basic building block drawn for a three-punctured sphere as the underlying Riemann surface, where, okay, here in these corners, it's a little too small. In this slide, we have punctures. These orange crosses, they signify branch points. And then there's a puncture of at infinity, if you want to read these pictures more precisely. So you can, in a relatively generic type of situation, you have the situation that what emanates from a branch point always falls into one or another puncture, like here. So it goes into either this puncture, or it goes off to the puncture at infinity. But there are different ways of doing that. So it can fall, well, it can be that the puncture here attracts all the Stokes lines from the branch points and so on. So in this case, the Stokes graph defines a triangulation of the Riemann surface. And yeah, that is a useful thing to be to note. There is a somewhat non-generic case where the Stokes lines close up and run, for example, from one branch point to another, or form closed trajectories in other ways. This is what we call the Fenchel-Nielsen case, or Fenchel-Nielsen type Stokes graphs, which plays a very important role for our story. But of course, all should be seen as, well, part of a unified picture. I mean, this appears as simply at special loci in our moduli space B, which are of particular importance because, yeah, I mean, these are the places where weak coupling expansions can be associated to. In between,
for chi's, right?
Can you say again?
We're trying to solve for chi's. Is that what we're doing here?
Chi's, you mean chi? Oh, these chi's here, yeah. So Okay, so I mean, just in terms of these pictures, it would say, for example, here in this diamond, we have a region where chi's are defined and Borel summable. So here we have and then, for example, here we also can define a basis of solutions to our differential equation by Borel summation. So there's a very canonical way of doing it, which in particular would fix normalization issues once we have basically chosen here the leading term. So these are very special solutions, which are basically as canonical as possible, defined through H-bar expansion.
Okay.
Whereas in general, of course, well, I always have a choice of a basis and choice of normalizations of the basis elements of the space of solutions to a differential equation. Okay, so if I restrict attention to the case of this FG as for Goncharov, because in that case, well, we have a triangulation. There is a well-known way of then defining coordinates xi, xcheck I in terms of these Vora symbols, where we just would need to take the curves beta here, which define the contour of integration, to be cycles which would encircle, say, pairs of branch points, changing the sheet through branch cuts, which are not drawn here in this picture. Okay, so there is then basically, well, a simple choice of the contours beta, which define the Vora symbols to produce closed contours, defining the coordinates here as, yeah, basically, I mean, a way to think about it is that this is deforming periods, right? And it's H-bar deformed through these series. And so it defines quantum periods, and that's how they're often called. So, and in particular, it is a mathematical theorem by Dylan Allegretti, who has proven a conjecture of Tom Bridgeland's, which is that the so defined coordinates are solutions to this so-called PPS-Riemann-Hilbert problem as defined here. What is important for our story is basically that this needs to be completed by well,
Joerg, I lost you. So in each of these chambers, we'll get an exact solution for the pair of chi's, one on each sheet of the Riemann surface. Right? They're like our brain amplitudes, right?
Mm-hmm.
And I mean, to go from that to actually understanding monodromy, I mean, how to patch them all the way across. How do we patch them across the cuts?
Well,
I mean, across the...
To build a monodromy out of these coordinates xi, that is basically the business of this abelianization. You would then have to, in fact, so you have a basis defined here, basically in each of these regions, like here in A, right? So we have a decomposition here in 3 regions, but of course, in general, you can imagine it's going to be more complicated. When you cross here the Stokes lines, what's going to happen is the Stokes phenomenon, that is, jumps happen for a basis of the solutions that are defined by exact WKB. And this, these jumps then basically, yeah, what these jumps describe is how the different bases associated to regions by the exact WKB are related to each other. And from this, you can build a monodromy by just computing the parallel transport and picking up these changes of basis for each crossing of such a Stokes line.
But this is not, I mean, even for simple differential equations, exactly in understanding, even if you have exact solutions, how they patch up across is not simple, right?
No, it's not at all simple. No. I mean,
but you're saying in principle this can be done, or is this something that you actually have solved and you can actually write down the?
No. I mean, here in this story, there's almost nothing that is explicit, right? It's more like proof of existence. Okay. So what is known is indeed are two things, and that is part of here what Allegretti has proven, relying on earlier work, is on the one hand sort of the description of how the coordinates defined by exact WKB jump when you cross a Stokes line. Well, that is old, it goes back to Walsh and so on. And then the other thing is when you start moving on the base B, then the topological type of the Stokes graph can change, right? So for example, it can happen that, there's basically the flip phenomenon, which is that the type of Stokes graph can change as function of the underlying quadratic differential. And what this induces is the change of coordinates, which then, and this goes back to Delabar, Pham, and so on. It can be proven to be exactly of this cluster-like form. But these are all pretty non-trivial, but essentially already known results in the theory of the exact WKB. And what is quite non-trivial mathematically is, of course, having, for example, really the control over Borel summability, etc.
But the jumps of chi's are across the walls in the moduli space.
Yes.
They
happen. Then they can happen either as function of h bar or as function of q. I mean, after all, part of that is kind of trivial because you can always trade a phase rotation of h bar for a phase rotation of q, right? Okay. So that they must be related is trivial. So that they must jump as function of both is also pretty trivial.
Okay, I want to ask you this. It's very late in Europe, and you only went through half of your talk because of us. So I wanted to ask you, we can of course keep going, but if you want, we can do part 2. Like split it up in some way, if you'd like. Because I don't want to keep you up we can stay, but I don't know about how you feel.
I mean, good. For the moment, I'm fine. So, I mean, I can go on for at least a little while. But of course, on the other hand, maybe you are getting tired and maybe some digestion might also be helpful.
I'd like to really understand what you're doing. So I don't want it to go fast, because then I won't understand anything.
No, for the moment, I'm fine. So if you want me to continue, I certainly can at the moment. Okay, so good. I think where I wanted to continue was stressing a little bit that there is part of a relatively recent math story here which enters, which is basically the relation between Vorer symbols and Fock-Gontchoff coordinates, and that is due to Tom Bridgeland and Dylan Allegretti. And I think a bit that we add to this story is that one should also think about the Fenchel-Nielsen type graphs like here and the associated coordinates, which would then be of Fenchel-Nielsen type. So instead of triangulations, they would be associated to the Pants decompositions that you find that would be canonically defined by the graphs of this type. And the associated coordinates can also be defined through Borel summation, although, okay, there are some fine points I, for the moment, would like to skip. In essence, I think, or morally speaking, the story is quite analogous, but replaces here the triangulations by such Pants decompositions, again defined by the Stokes graphs of a Fenchel-Nielsen type. What is quite interesting, and I think this is what gives us, the remark I want to make, I guess, is that you should think of these Fenchel-Nielsen type coordinates and the corresponding graphs as being a natural completion. I mean, first of all, of course, they happen simply at particular loci in the base manifold B. But when you approach them, interesting phenomena happen, like, these Stokes graph getting twisted in a very complicated way. This is the phenomenon that Gayotto-Murnitsky called the juggle. I guess one of the sort of moral points I want to sell here, which I don't really have the time to discuss, but which I just want to state, is that you should think of the Fermionian type coordinates simply as limits of Fock-Goncharov type coordinates. They are basically on a very similar footing. I mean, in the way they were traditionally defined, this is not at all clear. But in this way of thinking about it, it is becoming pretty clear that really you want to consider them on an equal footing, and that these Fermionian type coordinates just are limiting cases of a sort of the Fock-Goncharov type coordinates. I can be more precise about this, but I don't want sort of to spend too much of time on this. Okay, so now I'm coming, and at least this bit I should perhaps finish in a reasonable way. Well, the main part of the proposal, which is that there are a line bundle on our space M defined by difference generating functions representing the transition functions, and the connection then defined essentially, well, defined or defining the tau functions that we're after. And then there's again this magic formula, which I like very much. So, well, I want, good. Here, so the point is that this means simply that if I have a tau function on a patch like ui, and if I have a tau function on a patch uj, then there is intersection. If there is intersection of the charts of the patches, then there should be a relation of this form. And what we need to describe is what are these guys here? The Fij of xi, xj. Here you may already see something.
And also, what are my what are the patches?
Right, the patches. Yeah, okay. All this needs to be described, but all this has an answer in our proposal. But first, I want to describe what these here are. Here you may already see something reminiscent of generating functions, right? So if you have Poisson geometry with pairs of conjugate variables xj, xjj, then generating functions should take half of the old variables, like the xj's, and half of the new variables, and this is what they depend on. But the Fij are not strictly usual generating functions, but difference generating functions. What does that mean? Okay, first let's do a very simple but important observation. The very existence of such an expansion is fully equivalent to a pair of functional equations for the tau functions with respect to the variables x, right? Because it is clear if you have it represented as a Fourier series, then the result is periodic under shifts of x-check variables. And due to the particular form of the dependence here of the Fourier modes being here in this, well, difference in the argument, shifting the x variables by delta r of the tau function produces a factor which is exponential of the check variables. So this is just equivalent, right? So if you have, I mean, any function that satisfies these difference equations here with respect to the two types of shifts has such an expansion, and vice versa. Okay, so we want basically, and this is a very strong restriction on the type of coordinates we can put on our manifold, and we're claiming these, say, coordinates we're discussing here do satisfy these restrictions. Yeah, this is that such expansions can exist. If we would just take a random redefinition, say, of x checks, we would destroy this in general. Anyway, the main point here I want to stress is that when we now consider the change of chart, then of course the validity of such difference equations ensuring that there exist such expansions must be preserved or should be preserved. So we shall be considering coordinate changes from one patch to the other, such that these equations here, which describe, say, the xi coordinates, can be solved to express x check j as a function of xi and xj. So that such, this is like, well, textbook generating functions. And then we consider the possibility to have changes of, to have relations between the tau functions of this form. And now this simple and basic and important observations is, in order to ensure that in the both patches these difference equations hold, of course we have to impose conditions on these transition functions here, which are these, right? So if I shift the xi by delta r, that is, the vector which has at the rth place 1 and otherwise just 0, then it should spit out a factor e to the 2 pi I x check I r. If I do it with the xj coordinate, it should be the x check rj. So this is closely analogous to, of course, the usual definition of a generating function in Hamiltonian geometry, except that, what used to be taking derivatives is finite differences, and instead, and we're having here exponentials of our basic variables in these relations. But otherwise, it's of course closely analogous. And the whole reason why is that we want to make sure that in each patch we have such expansions. And this is a very restrictive property, if you think about it. So, okay, this is then what explains or justifies this name. This is what we call difference generating functions. So such things, this type of generalization of the usual generating functions, which is just exactly what we need here, because this is, somewhat fundamental. Okay, so here, maybe I skip it or just say very few words. If you want, you can go through the slide and check the calculations to see how to compute your first difference generating function, which is really the one for the flip, that is the change of the diagonal in a rectangle, where we have this type of relation between the coordinates, that is this type of symplectomorphism describing the change of coordinates. And you can simply check that you can build your difference generating function from Barnes double gamma functions, because they just solve exactly the type of difference equations that we need, simply due to the fact that the Barnes double gamma function, when you shift the argument, spits out a gamma function. And if you then have combinations like this, you can get something which spits out sine functions, or which then give factors like this here. So it's not black magic. So in particular, what we learn from that is how concretely such difference generating functions can look like. Here is the answer. They are relatively simple things built from Barnes double gamma functions, or G functions. Is
a unique solution? Up to
the solution. Okay. Well, good. I don't really have a theorem here, but I believe that really the thing which does the job for us here is absolutely unique. So another remark that is worth making perhaps is, in the end, this thing is also related to the dialogue. And that is also nice because of some relation to the work of Boris Piolin et al. The whole thing can be written in terms of the Rogers dialogue, and I think this has a deep meaning. Okay, at least some kind of conclusion I'm slowly reaching now. So this is sort of then the summary of what we've done. So basically, in the recent work, we explained how to define the solutions by basically combining exact WKB with Fermion conformal fluke theory. Basically, the exact WKB, what it tells us is to build the proper, or to build canonical solution to the equation defined by the quantum curve. And then if you wish, having these solutions at your hand, the CFT gives you a canonical way to build tau functions out, I mean, with the proper normalizations governed by the solutions to the equation defined by the quantum curve. That is very schematically the way it works. And yeah, and this we can do basically wherever we are in B, because we just, well, B is represented by a quadratic differential. It defines us our Stokes graphs. It defines us then the regions in the topological type of Stokes graph, defines us the regions in B in which we have one particular type of, or one particular system of coordinates. When the topological type of Stokes graphs changes, there is a change of coordinates, and we know how to describe it, and so on and so forth. And we can do it both for Kontrov and Fermion type coordinates. That is, this is the picture to have in mind. We have the space B. To each point B, which is a quadratic differential, we associate the corresponding Stokes graphs. Nothing happens. We have one system of coordinates as long as the topological type of Stokes graph is unchanged. When it does change, there is this wall crossing, and we have a change of coordinates associated to it. So that's roughly how it works. Yeah, and the proposal that we get is backed up or checked with topological work.
How does one recover the tau from the? So far, explain how to get the coordinates.
Yeah.
How do I get tau? I know how tau transforms, but how do I get tau in one patch?
What the CFT allows us to do is basically to build a tau function associated to a particular solution to the Riemann-Hilbert problem, which is defined by the exact WKB solution to the equation of the quantum curve. So this is basically what we have to, well, okay, how shall I describe it? Right, okay, a rough way or quick way of describing it is what is available when we have these Fermion type things where we have a Pans decomposition. Because what the exact WKB allows us to do is to have basically a particular normalization, a particular basis for the solutions to the quantum curve in each pair of Pans that we have in a Pans decomposition. And this then fixes the normalizations, basically the 3-point functions associated to this pair of Pans. And all the rest is basically done by factorization, by summing over intermediate states. That's sort of the, I mean, CFT just is the machine defining in this way then the tau functions. I mean, it gives us a canonical way to define the tau function associated to the solutions of the quantum curve in the pair of Pans appearing in the factorization.
You solve the whole thing by breaking the Riemann surface in C, in the Pans.
Yeah, but I mean, this way of breaking is determined again by Q, right? So it's determined by where I am on the base.
Sure. But is it fair to say that you're basically just showing that whichever solution you get from the CFT actually satisfies these relations, rather than saying that, well, I can actually find tau just from the data provided?
No, okay. I mean, so somehow the whole point of the game here is that, well, in the usual definition of the tau function, by just the differential equation, what remains is a normalization freedom. It does not fix the dependence on the xi and on the xi check. What all this business here with the symplectomorphisms and GMN and the jumps and the wall crossing is all about is fixing this dependence in a canonical way. Okay, so this is the leftover freedom that you have when you know it's a tau function in the usual sense. It is the freedom to multiply this tau function by an arbitrary function of xi and x check I. So what the usual definition of the tau function determines is the dependence on the complex structure of the underlying surface, or the dependence on what is called the times of the isomonodromic flows. It does not determine this here. This is a freedom. And here sort of we're supplying the other half of the coin, namely we're fixing the dependence, which of course for topological string applications is absolutely crucial. We're fixing the dependence also on these variables. We're fixing all the normalization freedom. And this is really the job that this business of wall crossing, symplectomorphisms, jumps, difference generating functions, and so on does, that it specifies a very precise way of doing that. And which step, where do you actually fix this? I mean, saying you can multiply by any function of x or of x check, that's a huge freedom. There's lots of functions. Yeah. Where do I fix that? Okay, yeah, this is some part which here I haven't included. I mean, on the one hand, of course, what this makes clear is it suffices to fix it anywhere in the moduli space, right? Any weak coupling regions or so. You may, yeah, but that's right. So then the rest sort of just goes. You see, when I wrote this paper long ago with Clement and Bouchard, the starting point of this paper was a naive idea that shouldn't it be true that, you know how Seiberg and Witten, they solved Seiberg and Witten theory by saying, oh, well, I know that there are special points in the moduli space, I know monodromy around them, and then that fixes everything. Shouldn't it be true that there's something like this at the quantum level? So one would hope that there's something like that at the quantum level, where you basically have just topological data. Okay, maybe you need much more than just monodromy. You need like to know all the BPS numbers or something. But yeah, well, no, it is very similar in spirit, right? It is very similar in spirit in the sense that, well, the prepotential a la Seiberg and Witten was defined in terms of the solution of an auxiliary Riemann-Hilbert problem, right? Which then was defining the periods. Here, basically the role of this Riemann-Hilbert problem is taken by the so-called BPS Riemann-Hilbert problem. And furthermore, and I think this is also kind of interesting, is then we have to fix it in one region. And what does the job is exact WKB. That is part of what we're doing in our paper is to use the exact WKB, but then ultimately it reduces to the pair of pens where we just, oh, sorry, my voice, where you just need the solution in the pair of pens and the exact WKB. And fortunately there are results by Iwaki and collaborators which tell us the normalization constants for the solutions to the quantum curve in the pair of pens. And then what we can, using, well, the formalism of tau functions and so on, compute is basically the corresponding normalization factors in the tau function. This is exactly basically these pieces here, the Z in and Z out pieces. Right, so these are basically 3-point functions, and there is, well, basically canonical relation between the these 3-point functions and the normalization of the solutions to the quantum curve in the pair of pens, and we've worked it out, right? So, and with this, everything is fixed. So that's the way it works, and this is the way sort of you can make it, in principle, effective for as complicated cases as you like, but there is of course a kind of bootstrap or so type of thing involved. I mean, after all, the functions that are defined in this way, these tau functions, these are reasonably complicated, and nobody really expects them to be sort of fully explicit in the end. I mean, people were already rather happy to have this combination of, I mean, for example, to have expansions for the tau functions as are provided by AGT, thanks to this Lisovie's observation.
Okay. Okay.
Good. Okay, so here it is already a partial summary slide. So this proposal agrees with topological vertex calculations on the real slice. This is the Fencher-Nielsen cases, but it extends it beyond it and say analytically, quote, quote, extend it all over the moduli space. And this can include, for example, strong coupling regions where the usual expansion and this Nekrasov type expansion of the partition functions doesn't work. There are other expansions were for the case of pure Seiberg-Witten first found in the important work of Itz, Lisovie, and Tücki. Good, but yeah, on the model level, sort of the main point here I want to stress is that the exact WKB for quantum curves fixes the normalization ambiguities. That is, this is what makes the H-bar deformation as canonical as possible. And this is what allows to fix here in particular the dependence of tau functions on monodromic data to the very end, which is also mathematically, I think, a new thing because the tau functions were usually, I mean, this was considered to be a standard ambiguity in the definition of the tau function. So what we're saying is there's a basically canonical way of fixing it that appears to be relevant here for this problem. Okay, so here is, well, first summary slide. So another more way of phrasing it is that the high genus corrections of the topological string are encoded in a canonical H-bar deformation of the moduli space of complex structures on the mirror Y of X. And good, I want to mention that there are several hints that this may generalize beyond the class sigma cases. In particular, there is a, for me, rather striking relation to work of Pulin et al. In fact, they have arrived at, I think, essentially equivalent proposal for the characterization of the topological string partition functions or of the tau functions as sections of a line bundle. Independently, thinking along completely different lines, namely thinking on how to describe NS5 brane corrections to the geometry of the hypermultiplet moduli spaces. But you can translate what they have proposed really precisely into what we have found in a completely different way by simply, for example, going to this example here and just doing a very simple change of normalization for the tau functions, in which has the effect that here the difference, what we call difference generating function, becomes basically Roger's dialog. And then that is the transition function that appears in their proposal for NS5 brane corrections to hypermultiplet moduli spaces. So in some sense, we've rediscovered it, but from a very different perspective. And furthermore, well, it seems their proposal has rarely been tested or verified or proven in particular cases. Here we can offer a whole class of cases where then putting things together, their proposal can be verified and made more precise for the first time. Well, also this relation to the geometry of spaces of stability conditions and so on, which is basically built in and well, which is being developed in the program of Tom Bridgeland, also gives me some hope that the story that we have can generalize. And there is the relation to determinants, Fredholm determinants, and so on, which indicates that there may be a relation also to the perspective or the proposals of Marcos Marinho et al. So all this I take as, well, supporting the hope that this can that this can generalize. This here could be a point to stop, as indeed it's getting late a little bit. Let me nevertheless advertise, if you want either to ask further questions or to go on a little bit in the discussion, or some chances for some other time for discussion or whatever. There's 3 points which I could tell a little more about. One I have included, so here this is elaborating a little bit the relation to Boris Piolin et al. But here is something that I included, or I have a kind of backup slide just for whoever is interested, which makes clear a relation to, well, that this deformation, this H-bar deformation, actually secretly is really a quantum deformation, making, I think, contact with other ideas of Mina and collaborators. Because
wonderful if you came back and gave us maybe a second part of the talk where you can maybe add some examples and then continue the story, so we don't rush through it. I think it's a beautiful, this story. It's an old problem, and so I don't.
Yes, okay. No, that should be no. I'd be happy to do that.
Great. Yeah. Okay.
I'd be happy to do that, and maybe then it's just okay. I mean, of course, we can.
We can continue where you stopped. Let's go out to the beginning. Yeah. Okay.
No. I mean, I can still. No, therefore, I mean, you suggest me maybe to stop for today, which is fine with me. But I can certainly take some further questions, but do not continue with the slides for now.
Could I just ask, you mentioned on the next slide a relationship between the work of Gross, Hacking, Kiel, and Siebert. Could you, or maybe the next slide after this one?
Yeah, okay, that's this part. Okay, so, well, I think, I think you had it in your recent papers, right? That there is a relation between the BPS state counting problem. I mean, in the case of hyperkähler manifolds, at least, like K3s, like you studied, there is a relation between the BPS counting problem and holomorphic curve counting problem, which I think is what explains some of the remarkable, well, similarities, if not relations, between, on the one hand, this GMN story, the reconstruction of hyperkähler metrics from the data, essentially BPS states, with this formalism that Kontsevich, Soibelmann, and then Gross and Siebert developed for the mirror symmetry problem. And well, I think, but well, okay, now I think really it's a matter of how much time I should talk about it. Maybe we can return to it at the other occasion that Mina has proposed. So it seems indeed here is an example where this becomes concrete and in fact related to our story. In the sense that there is a recent example that Pierrick Bousseau has studied, which is the cubic surface. He basically described the higher genus deformation of the mirror of the cubic surface that has been computed in the context of the Gross-Siebert program in some recent paper of Gross, Hacking, Kiel, and Siebert. And yeah, what he recovered essentially, I mean, they have this formalism of the theta functions, which are specific coordinate functions on the mirror that they construct in the terms of count of Gromov-Witten invariants. And he proved these nice relations for the quantum mirror, that is quantization coming from the higher genus corrections. However, now for the, here for the cubic surface. And yeah, he found something that we know from another context, that is the context being basically CFT and quantization of moduli spaces. And the point and the remark here is, in fact, good. We can define in CFT, a realization of this algebra in terms of the Linde line operators and so on. The remark is that this magic formula that I keep stressing again and again and again does something very remarkable. If we go at q equals to -1, with the q here, which is exactly this unrefined limit where all this story happens, then this transformation, what it does is exactly, it transforms the realization of this algebra here, the non-commutative algebra, into something, well, into something commutative. Well, it is commutative for q equals to -1 accidentally. So it transforms sort of a quantum story, which you have basically on this side of the equation here, which governs the z top, into a classical story, which defines the tau functions. And this classical story is what I've been discussing today. And these slides were supposed to indicate that, of course, thanks to this formula, thanks to this being an equivalence transform between two pictures of basically a quantum mechanical system, we can translate everything into z top proper, where then wall crossing relations are more complicated integral relations like this. And this is sort of how it is described really in the quantum world. And I think the quantum world is really what, thanks to these results of quantization of mirror symmetry, is what is produced by, say, higher genus mirror symmetry proper, right? So the Gromov-Witten world is here. This here is a little bit an auxiliary world, which is understood through dualities or through Donaldson-Thomas and so on. But this relation here really, in some sense, is the mathematical expression of such dualities between these different stories. Okay, these are probably rather opaque, confusing words. I'd be happy to expand and deliberate, but maybe we should take ourselves a bit more of time.
So, okay, let's first thank you, Joerg. We owe him lots for staying so late and giving us a beautiful talk. So, okay.
Thanks.
But I mean, this. I very much hope you'll return and we can continue the discussion. But it seems like it always smelled like that. What one should do is somehow do to get the closed string of some x, one should do the open string of its moduli. And this smells more and more like that, like open topological string of its moduli space. This smells exactly like that. The story of hacking and Kontsevich and so forth is about open string, not about a closed string.
That's right, yes. And of course, yeah, there is a confusing point here, which one shouldn't hide. I mean, this here is the mirror symmetry applied to the moduli space of the complex structures, right? So this is what you just referred to. There's of course a more basic one, which is the mirror symmetry of the local Calabi-Yau that we started from, where well, this business of non-commutativity would have a very simple effect in relation. It would just lead to the quantum curve. And understanding the whole story from this perspective, I think also is a story of understanding relation between open and closed topological string theories. And for this, I think, well, this very last slide here would be relevant because, I mean, there's on the one hand the partition functions, but we could also really talk about two-point functions or free Fermion expectation values, because they're going to be really just the expectation values of the free Fermions that appear, I mean, that define the tau functions in our story, right? So there's a relation. I mean, the tau function would be this overlap, and the expectation would be this overlap where you just insert here psi bar psi. and normalized by the tau function. Well, so this, of course, would be the thing that is associated to the closed string, and this is the thing that is associated, well, where we're decorating it with the open string. We can map everything here through this transform. So the story is kind of simple, and really we're having free fermions basically here on the left-hand side of the transform. The thing gets more complicated, and in a more serious, in a more clear sense, quantum on this side. Because on this side, what the size would become would be degenerate fields in the Virasoro conformal blocks and so on. The monodromies are more complicated. So the sort of quantum nature of the story is more clear on this side after, or basically undoing this transform, right? So the role of this transform is somehow to hide some of the quantum aspects. And anyway, I think maybe I'm getting tired and I'm not explaining very well. But in any case, I think one of the things I'm trying to say here is that there appears to be a canonical way of basically, but no, I mean, introducing here these degenerate fields or fermions as probes may be very useful to understand why the quantum deformation on the open string level, which is what describes the quantization induced by higher genus corrections of the mirror curve, right, which becomes the quantum curve, why this quantization induces the quantization on the closed string level, on the level of partition functions that we have discussed. Because in the sense of 4D, 2D wall crossing, they're intimately tied to each other. The consistency for the 2D wall crossing are the 4D wall crossing relations and so on, right? If I want a consistent picture of the 2D wall crossings, which is consistent all over the moduli space, then it induces basically the jumps and the 4D wall crossing as described. That is sort of roughly the claim I'm trying to make here. And so in some sense, yeah, in this sense, these probing it by free fermions or by extra brains, by probing it with some open string sector idea, combined with the idea here of the 4D, 2D wall crossing appears to be very fruitful. And well, in work in progress, I hope to sort of flesh out this point of view in more detail. So some of the outlines are pretty clear already, but this is not yet really what is developed in our recent paper. Yeah, certainly these two formulas that you have should tie into this 4D-2D story. That's true. But yeah, I think that there's something else is going on. I mean, there's an additional level of open string of the moduli space, which is something else yet. Oh, okay. Yes, I think yes, right. That is probably okay. Yes, concerning this story here. Yeah, yeah. When you do the open string of the moduli space, there's no gravity, but there's also no Calabi-Yau because you're on the moduli space. So interesting. Okay. I mean, okay. This is a point I myself like to understand better. I mean, I note, yes, indeed, there is such a thing going on here, but I don't really understand it very well yet. Joerg, thank you so much. And I hope we can plan for, let's just find a good time for you to come back and we continue. Okay, yes. Okay. Probably then it doesn't have to be that long, so I apologize for it. It doesn't have to be that long. So in fact, short is better, so. Okay, but no, thank you very much for the. Sorry, I just know what I meant. I meant in terms of the time until you come back. I didn't mean okay. How long your next time. No, I guess in this way, yes, it should not be a problem. I mean, next weeks are going to be a bit busy, but anyway. We spoke about different things simultaneously, so it came out very long. All right. Right. Joerg, thank you. Thanks so much, and thanks. Yeah, thank you for the invitation again, and yeah, hope to see you again. Not too far in the future. Right. All right. Bye-bye. Thanks, everyone. Okay, bye-bye. All the best. Stay healthy and so on. Likewise. Bye. Thanks for the taxi story.